Mike asked me to talk about CHERI performance. It's in the hardware track, though we're not mentioning just specifically hardware here. I will mention about performance, but not just. Really, what I'm also going to talk about is commercialization, and really what we need to think about as we transition CHERI from being a research technology to being a commercial technology. So I thought everybody would have enough about chips and everything else, so I'm going to start with cars. So I'm in the market at the moment to buy a new car. Whenever we start thinking about cars, we obviously think about the best possible car we could have. So yeah, I'd love to be able to get a car like this, but realistically, I'm pragmatic. I'm going to end up with, a car that will do what I need it to do. So, so if I was buying a car, well, I'm going to ask you, what sort of things do you think I should be considering if I buy a car? Any ideas?
Safety and security.
Oh, excellent. And I didn't prime them, honestly. Yes, yes. Something that works, yeah. Anything else? Speed and power, performance, yeah. I mean, should have got that from the top. So I'm going to pick a few of those. So obviously things like fuel efficiency, speed, price is obviously going to be a big issue for everybody. Safety, security, thank you, Tarek. And delivery time, because I want to get my car on time. Now in product management, there's a concept or a theory called job to be done. So, and the theory is that people buy products that meet their needs to do something specific. So if I'm in a market to buy a car, I'm not just buying a car. I want it to do something specific. So as an example, if I lived up a mountain, up some dirt track road, and I want to be able to use my car at all times, I'd get a 4x4. So I'd concentrate within the sort of area of those features that I was looking at on power, for instance. And just to go back a minute, whenever we look at each of these sort of things that I'm judging a product on, they're not independent. So for instance, if I want more speed, fuel efficiency might be less. So there's a design space I have to work with. Again, if my job to be done involved shifting lots of stuff around, then I might want a pickup truck, has a different design space. If I wanted maximum performance, if my job to be done is getting from A to B, but as fast as possible, then we have a different set of parameters within our design space. And when you're looking at commercial products, we can sort of generalize the job to be done, and then we create products that target each of those. So there's also obviously going to be jobs to be done which are well outside of what we had expected as product manufacturers, for instance. And these become bespoke solutions. Well, so sort of things we need to think about. So if we have products from different manufacturers and they meet the job to be done, but obviously one has like lower performance, higher fuel costs, would you buy it? And obviously the answer would be no. Now I've been talking about cars obviously, but of course we're here for CHERI, so we want to relate this to semiconductors and electronic product development. So we have sort of analogies between what I would select in a product for a car and what I would pick if I was designing an electronic product or if I was getting some IP from a IP vendor. The main ones we concentrate on, the sort of key headlines one that we need to have to get through the door are power, performance, area. So power is, effectively efficiency, performance, how fast we can compute stuff and can we do it within the amount of time that we need it to. and in silicon cost, area equates to price. Obviously then we have safety, security and schedule. Now as we transition CHERI from being a, it has been in research a long time. From what we've heard already in the talks, we can see it's starting to become commercialized. And one of the things we have to start thinking about is, because of the jobs to be done idea, is that CHERI may not be the only solution. We're all here very focused on CHERI, but we need to start looking at the wider view as well as we move towards commercialization. So what we're going to have to do is make sure that our products with CHERI are competitive with other solutions that are out there. So this is a sort of call to arms to start thinking about what we need to do to ensure that CHERI continues on and becomes a commercial success. Because if we don't concentrate on these things, then, well, taking the car comparison again, if there's something out there that meets our job to be done, then CHERI may not be the solution that people pick unless it's competitive. So I'm going to concentrate on performance here. Compute performance. So one of the things, I'm just going to go through a range of things that we're looking at Codasip to improve the performance and to dispel some of the myths as well that there has been about the CHERI performance. So we'll start with the hardware. One of the things I would say is we need to start designing for CHERI. So a lot of our cores at the moment have been retrofits on existing cores, but of course these come with their initial constraints as well. So we do need to look at things like making sure that the bus widths, for instance, are capability sized, and we need to think about the pipeline, how we optimize that specifically for CHERI. Within Codasip, whenever we're designing our next generation of CPUs, for instance, we're working at the very early stages, even well before pre-silicon, to design for CHERI. So we're taking workloads, we're feeding through traces, we're running it then through a software model of microarchitecture, and we're looking to see how it performs, and then we tailor it to get the best performance. Obviously, whenever we're doing performance optimization, we should always be making data-driven decisions. Not just what we think will do good, but actually feeding through real stuff and seeing. So this is just, I wouldn't call it a toy example, but one of the things we were doing, for instance, is running through mbench tests through it. We have quite a wide range of things we're running through the model, but actually mbench is a good way to demonstrate the diversity of the workloads that go through a CHERI system. So each one of these is a different benchmark. This is just a selection of CHERI instructions that it's using. And you can see even in this small subset that there's a very wide range of behaviors that we need to consider going through. So the next thing we need to consider is that CHERI is not just a core. So we have a core, but there's also bits outside of CHERI, such as the memory tagging system or potentially revocation as well. So we need to be thinking about the impact of this, particularly on fixed width memories like DDR, for instance. We don't want to be able to, or we don't want to be introducing delays in the performance due to memory accesses, for instance, just because we have to deal with the tags when it goes to DDR. So, and again, our workloads are very diverse in terms of how many capabilities they use compared to how many integer accesses they do. So again, this is mbench, and this is a comparison of load and store accesses, capability versus integer access. And, to be able to optimize across the board, we have to consider all different types of workloads. The other thing where we may want to get more performance is actually from the ISA itself. So whenever we looked at the CHERI RISC-V ISA, we want it to be basically a good, solid subset of instructions, but it may not necessarily be the most efficient or effective instruction in there. We may want to combine instructions, for instance, to get more performance out. There's also evolving use cases that we have to track. As CHERI is used for more and more things, then we may want to actually adapt the ISA to come up with special cases if we need to. And CHERI is very much a hardware-software co-design technology, so the choices we make at the ISA influence the hardware and vice versa. We have to take that into account as well. The compiler, we've been doing a lot of work on the compiler as well. We're obviously trying to make best use of the ISA. It is microarchitecture specific to a point as well. So, for instance, one of the things we've been looking at recently is our X730 CPU, for instance, is a dual issue machine. And by just implementing the scheduling model within the compiler, we can get very significant gains. So we're improving the compiler to match our microarchitecture. So, I mean, it can be up to 50% improvement in some cases. So, and again, very workload dependent. The other thing, maybe for performance, is can we use the hardware more effectively? So, for instance, we have these very wide registers now. Can we make more use of those registers within the register file? If we're using integer operations, for instance, we're only using the lower 64 bits. Is there something we can do with the upper 64 bits? Could we fit SIMD in there, even having these nice wide registers? There's plenty of options here that we can look at. Software as well. Well, we've been doing a lot of work optimizing the software. So particularly around common functions libraries and things like string libraries, for instance. These are sort of things that are generally applicable, and we need to, improve them so that they work better with CHERI. And obviously our software must be easy to use. There's also what can we remove from software when we have CHERI. So we may be doing checks in there for, buffer overflows or something that we may be able to remove, either at the language level or at the application level. So the sort of results we're getting at the moment, so this is where we are. Generally, we're finding CHERI, all the concerns that CHERI would significantly slow our software compared to our non-CHERI version of the core are pretty much unfounded, actually. So we had some worst case examples in our benchmarks, and we've done much more benchmarks than this. We've got spec and other workloads as well, but overall we're seeing around somewhere between 5 to 7% decrease at the moment, though we think we'll be able to pull that up as well. And of course the other thing is that, if we're running an application, I was mentioning things you can remove. So a lot of the software today is compiled with things like software stack protector, which, we don't really need with CHERI anymore. So actually the relative performance of what we can achieve versus what's already there is really minimal. And in fact, the worst case examples too, we know why they're happening, and we can deal with those as well. So I think it'll only get better. And final thing I'm going to leave you with is question, well, we were talking about jobs to be done. Is modern hardware and software up to the job that we needed to do now, as opposed to the job we needed to be done in 1950, as John sort of alluded to this morning? And can CHERI help with this? And actually, I think some of the work we're seeing at the moment with the likes of CHERI OS and other things show that there are things that we can now do that CHERI gives us the ability to do that we couldn't have done before. And I think ultimately that'll help with performance increases as well. Okay, that's it. Questions?
Carl, have you not actually looked at how compartmentalization is actually faster than page-to-table isolation, rather than just telling us the negatives of the loop?
I didn't want to mention that one specifically, but yeah, I mean, this is part of the thing. So one of the things I think CHERI can help with is breaking down these old abstractions and replacing them with better options, but like that, more modern, useful options.
You mind if I take it, just mention a quick thing? So, as you know, Research Centre, we've been working on compartmentalization in various ways. Codasip has kindly provided us with their hardware design on FPGA, which we're also using with several other designs, including CV6. And compartmentalization, benchmarking, and optimization and so on is a very active area of work right now. So, no graphs in my slides, but I think very soon we'll have a lot to say on the topic.
Yeah. Yes.
So you mentioned that you had an idea of why those poor performers are happening. What's the reason? Can you share that? Or?
From what I can remember, one of them's very heavily using global variables. It's horrible code to start with. Yeah, it's just there's some things we're not handling very well at the moment with the ISA that we have. So, and with the compilation as well. So
Is it a matter of rewriting the code in a better way, or?
I think yeah, handling it possibly better in the compiler might be an option. Yeah.
With that last question, what is the point at which you decide that this code is so bad there's no point in perhaps over-optimizing for it if that's the cost elsewhere?
That's a very good. I mean, it's one thing I should mention. It's very easy to select one particular benchmark and then optimize for that, when in fact what we're trying to do is optimize across the board. And you're right, I mean, that code is particularly bad, and personally, yeah, is it actually worth? It's also, benchmark is whether that would occur in real code as well, which is, yeah, I would hope not, but you never know. There's a lot of, yeah, variety of code like that out there in terms of quality. So.
Okay, so thank you again.
Okay,
Thank you very much.